photoelectric effect that Einstein did that described how electrons can be ejected from a metal by shining light sources on the surface. We talked about this when we learned about light emission spectrum, and we had the spectroscopes that we held up to the light, and we saw the different lines. Does that ring a bell? Maybe? We do it in like October-ish in Chem 1. Okay. So from this data, we can determine the exact energy of the photon required to eject an electron, and that energy is associated with the EMR spectrum, the electromagnetic radiation spectrum. And so it's how much energy the electron needs to leave the metal. It has to kind of do with ionization energy that we talked about at the end of 1.5. So the binding energy is that energy that's holding the electron in, and how much energy do you need to overcome that binding energy is what we can determine. So similar to the photoelectric effect is the photoelectron spectroscopy, which is PES for short. PES can be used to determine the relative energies of electrons in individual atoms as well as molecules. In photoelectron spectroscopy, high energy photons are directed at the sample, and the kinetic energies of the ejected electrons are measured. From this data, the energy can be determined by taking the electron energy, that's what E, electron stands for, is equal to H, which is Planck's constant, it's on your equation sheet, times the velocity minus the kinetic energy. Now, do you need to actually solve this equation for anything? No, we look at graphs instead for this. We look at the results of the data. For example, this is for nitrogen, a molecule of nitrogen gas, where when you have two nitrogen atoms and you have the photons hitting the atoms, there are three main areas of energy absorption that are shown right here, and right here. This stuff over here is called molecular orbitals. So if we have sublevels and orbitals for electrons, you also have orbitals for molecules, and that is beyond the scope of this course, and we don't have to teach it. But those energies are associated specific to match up with those orbitals in a molecule. Okay. When we see those energies, that helps us to characterize and figure out the energies of the electrons in the molecule. So the photoelectron spectroscopy helps us characterize and test theories of bonding in molecules. It's also useful for studying the electron energies. So this is the phosphorus spectrum. This is what we're going to see. Do you see the squiggly line? Okay. The way that we read these graphs is you always start at the higher side of energy, and you label the peaks, 1s, 2s, 2p, like that, okay? So we have example 16 to work through to see this. So I think I have it coming up on the next slide, but I just fit all the questions in one. So we're going to label each peak on the graph with the subshell that it represents, 1s, 2s, whatever. Then we want to know which electron will be removed to form the ion from our graph. Then we are going to superimpose what another element would look like on top of it. Okay? So anytime you have one of these graphs, you want to make sure that you start labeling on the higher energy side. So you look at the x-axis, because that is the ionization energy axis, and we always start on the higher energy side. So for this problem, it is on the left side. 75% of the time, the higher energy side is the left side. But you always just want to make sure and check, because occasionally it will be flip-flopped. Okay? So to label the sub-levels, we always start with, just like electron configuration, we always start with 1s. Now, so since this is the first peak on the highest side, this is going to be 1s, and that's all you have to write next to it is 1s. The way that you help determine the rest of the peaks and how many electrons are in each peak is based on the size of the 1s peak, okay? So 1s can hold how many electrons? 2. So this height right here represents 2 electrons, okay? So the next peak that we come across has the same height, so what peak should that be? 2s. Since it's the same height, then it's also 2s, because that would also signify that it holds 2 electrons. Okay? Don't worry about these lines on the axis. It just means that there's a lot of space, empty space in between, and they're just trying to shorten the graph into one page. Okay? So now we come to the next peak. Now, this is a lot higher, and like this is where our 2 electrons are. Could this, maybe drawn not to scale, but could this represent how many electrons do you think? 6. Because there's 2 reasons why you know it's 6. 1, because it is kind of 3 times this height, but 2, there's more peaks after it, so this orbital has to be filled. And it's bigger, so this would be which peak? What do we label it? 2p. Yep. And it holds 6 electrons. Okay? Then we have the next peak, 3s. The second to last peak is the same height as the 2p, so that would be 3p. Now the last peak that we have, it's not as high as the 3s, so it doesn't hold 2 electrons, it holds how many electrons? 1, because it's about half the size as the s peaks. So it only holds 1 electron. And what's our next thing after 3p? 4s. Now sometimes people get confused because maybe it's going to cut and the last peak you have is 3p, but it's that size. It still would be 3p, but it just depends on what the electron configuration is for this element. And we are dealing with potassium, okay? So that, and potassium ends in 4s? Yes. We did that electron configuration before in 1.5. Okay, so we did A, we labeled the peaks on the graph. B, which electron do you think will be lost when it wants to remove to become an ion? 4s. Yep, the 4s, so this is the answer to B. You could write B 4s if you want to, I don't know what you want to say. But we want to lose the electron in the outermost energy level, or the farthest away from the nucleus. You could always think about it that if you're starting with the highest energy, like think about this is just a representation or like a timeline model of how far away from the nucleus things are. So if this is the nucleus, the 1s electrons are closest to the nucleus, and the farthest away from the nucleus are the 4s electrons. So we would want to lose the 4s electrons. Okay, now, last but not least, C. We want to superimpose an estimate of what the spectrum of calcium would be on top of potassium spectrum above. So we are going to draw peaks to represent calcium's peaks, okay? But you have to be careful because calcium does have 1 more electron than potassium, and it also has 1 more proton. So that slightly changes where the peaks are located based on ionization energy, okay? So we're not going to draw the peaks on top of the other peaks. They'll be close to them, but not on top of. Do you think having another electron and another proton, it will take more energy, so they should be shifted a little right, or less energy, so they should be shifted a little left? If they're, yes, it does get bigger. Yeah. It's actually shifted a little left. And I'm trying to think about why it is that way right now. Because I'm drawing a blank. Even though it is slightly bigger, and it has. So wouldn't it be like, because what you said was like it's the farthest away? Yes, it is the farthest away, but it wants to hold on to one of the electrons for sure, and then the second electron lose later. I didn't make a note of why it's slightly left instead of slightly right. So, I'm going to need to tell you that tomorrow. Sorry. But, so the peaks that you're going to draw on are going to be the same height, but they're going to be shifted off just a little bit. So go ahead and draw your peaks on top, the same height, but slightly to the left. And then what about the 4s peak? What do you do with that one? Yeah, you make it 1 higher so that it shows that it has 2 electrons in there. So calcium has more protons than potassium, so with a higher nuclear charge pulling on the electron, the 1s electron in calcium should have a higher ionization energy because there's more protons that it needs to combat. So it will need more energy to keep it in there. So the peak should be left because there's more energy, and left is higher energy. If we look back at, who's gone back? Where is that from? So calcium has a higher ionization energy than potassium does. So that's